what are called as the deformation measures and their physical significance. 3.4.6. So deformation measures and their physical significance. Now, if you are thinking about a solid and deformation of a solid, what is the principal quantity of interest in for solids? Strain, right? If we have a component and we are applying some kind of a loading, the first thing we are interested is in change in dimension. So typically, we talk about for solids, the deformation or strain, and for fluids, anybody can tell me what is important for a fluid? Is it the amount of change in length or is it something else? Do you know? I'll give you a clue. What is Hooke's law? Stress equals Young's modulus times strain. What is Newton's law of viscosity? Shear stress is equal to viscosity times velocity gradient. I'm sure you have seen this in some form in your prior courses on fluid and solid mechanics. What is the difference between this equation, which describes the elastic deformation of a solid, and this equation, which describes the shear stress in a fluid?
E in small length and rho is viscosity.
Yeah, this is Young's modulus. This is viscosity, that is the material property. What is epsilon? Epsilon is strain. And strain is typically defined as change in length divided by original length. Right? This quantity du by dy, if you are not aware, is called the velocity gradient because it's like a change in velocity with position, but it is more correctly referred to as strain rate. It is like saying du dy is d of change in length over length divided by time. So it is also referred to as the strain rate. So the point I'm trying to drive home is, depending on what your material is, if it is a solid, you are more concerned about the strain or the strain tensor, which we are going to derive now. If you are interested in fluids, the more appropriate quantity to describe a fluid is the deformation rate or strain rate tensor. So we are going to derive both of these quantities under the heading of deformation measures. Of course, when we say deformation measures, we are now going to talk about solids, but hopefully next lecture we are going to talk about rate of deformations, which is more appropriate for fluids. Okay, so the math can sometimes be dizzying in the sense that you have to think about index and reference frame and then spatial frame and everything. But the gut of the instinctive understanding is to think strain means solid or solid means strain, and strain rate is the appropriate quantity for fluids. This is if you have that level of clarity, then you can work your way through the math. If you can do math, which is essentially what is this? This is if I tell you F, this is matrix multiplication. Did you come to this course to learn matrix multiplication? You want to know what these matrices represent, which is to intuitively understand what is strain and strain rate, which goes with solids and fluids. That's the thread of logic. Okay, so I think I can erase this side. So on Tuesday, you know what your question for the quiz is. So please either do the work that you're supposed to do today, which is to get the eigenvalues and eigenvectors, and on Tuesday you are supposed to take it one step further. Okay? But do show up. If you do this at home, you don't get credit for it. If you do it in front of me. All right. So we are going to calculate or look at what is called as the Lagrangian strain tensor E. Okay. E is defined as half of C minus identity tensor in material coordinates, or this is same as writing Eij is half Cij minus delta Hij. From where are we getting this? That's the question. Like I'm just throwing a definition at you. How can we understand or make sense of this definition, or how to interpret this definition? That's the question. Before I do that, just a quick recap, just to check where we are. What is F? Deformation gradient, and you get that as a gradient of the spatial vector with respect to the material vector, or you write this partial x over partial material x. Okay, and deformation, when we write it as RU or VR, what are we essentially doing? What is the physics or physical understanding of this decomposition? We talked about this last lecture. Representing an arbitrary deformation as anyone as a sequence of rotation plus stretch in material frame or stretch in spatial frame plus rotation. See, again, I repeat, the math will be kind of confusing. That's why I add these notes to help you understand what R represents and what B represents and what U represents. What does R represent? It is the rotation operation. So imagine that example I gave you about torsion. Torsion combined with bending or torsion combined with axial loading can be split as a rotation plus a loading or a stretch. Rotation is just change in orientation, followed by stretch is the result of some kind of axial load or a transverse load. So try to split any deformation into a rotation followed by loading or loading followed by rotation. Okay. So the reason I brought this up is, all right, you are getting a deformation gradient. You are even understanding or interpreting it in terms of rotation and stretch. Okay. At the end of the day, how do you convert this into a strain tensor or an understanding? If your loading is in a particular direction and if the deformation is also along that direction, this strain tensor should have an element which is like, let's say 1 direction. Its 1 element should be the strain along direction 1, a change in length along direction 1, right? Its 1 element should be change in length along direction 1 due to loading in direction 2. 1,3 element should be change in length along direction 1 due to loading in a third direction. The elements, 9 elements of this strain tensor should tell you to, should essentially tell you what is the change in length along a certain direction due to the loading in that direction, due to loading in two other directions. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. What is 3, 2? It's the change in length along direction 3 due to loading in direction 2. You should be able to look at this and first interpret this before you could do this right hand side math. What is C? F transpose times F. You know how to compute it now. You have to now understand what it means. Okay. I know it. Is there any question? If something is not clear, please ask. I don't want puzzling looks. I want a discussion.
So it's just representing, well, I thought E was representing the deformation, so why is C also? Is it because,
So this formula, okay, what I told in words is for the left hand side, that E11, sorry, I didn't say, I should have said E11, not C11. I wish I could go back and correct that. E11, E12, E13 is the strain in direction 1 due to loading in 1 and so on and so forth. How is that equal to this expression, that derivation we are going to do now? There's a few lines.
is the significance, I guess, is my question, really.
We'll see that once we see that few lines of derivation, it will naturally pop out. It's basically like the change in length dx in spatial frame is related to the change in length dx in the material frame through this term. This exactly will show up in a minute.
Okay.
What I am trying to put forward is this quantity is what you will seek if you are actually doing a measurement or if you are actually trying to calculate the response of a material to a load. What is the response of a material to a load? You apply the loading, you observe a strain. You apply a loading, you observe a velocity gradient. This response, we write this in scalar terms because it's just one axis, it's just one direction. We don't worry about what happens in the other direction. Now you know what happens in the other direction. If you write this for the axial direction, what is the equation for the radial direction and the transverse direction? You will have, if the length elongates by a certain strain, you know the transverse dimension will contract by a certain rate, a certain same value, which is epsilon multiplied by the Poisson's ratio. You know there is, what I'm trying to say is, even in a very, very simple case, which is uniaxial tension, the response of the material to uniaxial tension is elongation in this direction, but in the transverse direction, it is a contraction where the strain is Poisson's ratio multiplied by epsilon. So the simplest of case you can think of is still involving, if you write a strain tensor for this is epsilon, Poisson's ratio nu times epsilon. Would you agree with that? Like very simple case. Just one axis and loading along one axis. Every other axis there is no loading. So the third axis is just right. So you can write the other terms to be 0. This is just intuitive. What we are doing here is to be able to connect this eventually with the deformation tensor. That derivation, now we are going to start. Okay. All right, I'm glad you asked that question. Those are the kind of things that help me clarify. All right. Consider the change in length of a material vector. That is, if you have a point that is denoted as x, and if you consider the change in position, this would be x plus dx, and this vector would be x dx. So dx you can write is dxi ei cap. Can you? Like small change in length, differential change in length along direction 1, 2, and 3. Okay. So this is component of the change in position vector. So I'll write it out. Change in position. So some people just write change in position, where position is implied to be a vector. I just add the word vector explicitly because I want you to understand change in length is different from change in position. The change in length ds would be dxi square root, right? Like it is the magnitude of this dx vector, that is what we call change in length. You're with me so far, right? And you can make the same discussion for a point whose coordinate is x, and you have a, I'll just draw it differently here. So you have x plus dx, and the vector being dx. So you can write dx is equal to dxi ei cap in the spatial frame, and ds is equal to square root of dxi. Square root of dxi. So this is again change in length, but in the spatial frame of reference. What is the basic relationship that involves or that relates dx and dx material?
Deformation.
Deformation tensor. Vectors.
Deformation tensor.
I'm heartbroken. After all this discussion, you call it a vector. F dot dx. Okay. So you can write dxi is Fij dxj. That's what it means. Okay. So when I have to write ds squared, that is dxi. Okay. I'm going to represent, this is Fij, I'll call it Fii dxi multiplied by Fij dxj. We started this towards the end of last lecture, and the reason we do I and I, I'm sure you would agree with me that I can write this dx dot dx, which is dx dxj ei dot ej, which will be a delta function. It will again lead you to this. It will again lead you to this. So that's why I have the I here. So I can write this Fii Fij multiplied by dxi dxj. So if we consider ds squared minus ds squared. That is, if we consider what is ds squared, that is simply this, right? So this is equal to fii fij dxi dxj minus minus. Is it okay if I write this dxi dxj? The book actually, if you go to page 87, they do something. Page 87, you can go check this out. In one line, they write ds squared equal to dxi dxi. In the very next line, they write, they substitute for ds squared as delta ij times dxi dxj. Those two are equivalent, right? And where do we get the delta from? What is ds? ds squared is dx dot dx, which you can write dxi ei dot dxj ej, which will get you delta ij dxi dxj. That's what we just skipped and wrote it directly here. It's just going back and reintroducing the delta. So I can write this ds squared is equal to minus delta ij times dxi dxj. Now this is fii minus, sorry, multiplied by fij minus delta ij dxi dxj. What is the rank of this quantity? Rank meaning what are the indices on which this quantity will depend? This is I and J material. Here, lowercase I, spatial I is repeating, I and J are non-repeating. So this is the component of a tensor, component of a second order material tensor, because it depends on I and J material. Okay. So we are getting close in some sense that we are writing ds squared minus ds squared is fii fij minus delta ij dxi dxt. Sorry, you can take your picture now. Okay. So here, book introduces the definition E is equal to half Cij minus delta Ij. What I first want us to do is to show, you call this Eij. Eij is equal to half Cij minus delta Ij. Can we prove that? What is C? There is, you want to show this expression and this expression are one and the same. How would we prove that? First of all, what is C? F transpose times F transpose dot F. So you write F Ij is, that is F is equal to Fij Eij with Ei coming from spatial and Ej coming from material coordinates. What is F transpose? How do you write F transpose? So when we did homogeneous, that is, you write A is Aij, Ei, Ej. When you if you want A transpose, you would just flip the index here and keep this same. This would be Aji, Ei, Ej. Okay. So if we apply that logic, this is F. Yeah, you can say Ji, Ei, Ej. But when you want to multiply F transpose dot F, how will you do this? Let's say this is F I Fii Ei dot, and then I have F, which I'll say this is F JJ EJ material. So even though I've so this would be FII EI that is, I know this component here, it's a mix, it's a second order tensor in material terms. So this is going to be FII IJ EI EJ. But you'll notice here, this is II, this is the opposite of that. So what is the catch here? What are we doing correctly, or what are we missing? That this, you can see that this agrees, but this is flipped. What's the problem here?
Excuse me.
Yes?
That part you're writing, it's not visible for me, that
Oh.
part of the board.
Okay, I'll turn the camera. I'm sorry, I went too much to the right. Can you see now?
And the right part you were,
Oh, I'm
Right.
going in the other direction.
yeah, I can see.
Yeah.
Thank you.
So I want you to think, how would you write or how would you prove this quantity and this quantity are really the same? That's what the sorry, 2 times EIJ is this. So how are these two equal? That is the question here. Think about it a little bit, give me some thoughts. If we agree with this definition, then we can make interpretations. But before that, I want to know how this can be actually established. Is this our mistake? I want to go back to something that we've been doing since the beginning. That is, if we consider a transpose that is a tensor, if I take notes. So if you say a tensor A, this is shorthand for A11, 12, 13, 21, and so on. What is A transpose? A transpose has A11 here, 12 here, 13 here, 21 here, and so on. This is E1, E1, the diagonal. E1, E2. So what we are doing is keeping the dyad same and writing this as E1, E2. Okay. What is this here? This is A12, E2, E1. So this is the predicament we are having, which is if you consider A transpose dot A. How will that actually be calculated?
All
This would be row 1, column 1, A11 squared plus A21 squared plus A31 squared. Column 1, row 1, column 1, row 2. That will be the second element, right?
A11,
A11,
A1,
1, 2,
plus
1, 1, yeah, plus 2, 1, 2, 2, plus 3, 1,
A3, A3.
3, 2. and so on. The book says this term is Cij. I just want to make sure we understand why instead of just taking it and assuming it and just going. Okay. So I'm thinking, that is, I'm trying to think, I'm trying to ask you to think, how is this F? If C is equal to F transpose times F, how do we establish Cij is Fii, Fij, and not Cij equal to Fii, Fij? This is all I'm asking you to think or think through. Or in other words, what's the correct way to represent transpose? Okay, so little revisiting. This is from unit 1. If B of x comma y, where x and y are the two vectors that form the dyad, is equal to A of y comma x, then this implies B is the transpose of A. In initial form, Bij is equal to Aj. We have two tensors in our hand, F and then F transpose. Okay, F and F transpose. So if F is written as Fij, Ei, Ej, where you can say this is Ei and this is Ej. If B formed by a dyad X and Y is equal to A formed by the dyad Y and X, then it is they are the transpose of each other. That's what this statement means. So what is F transpose then? F transpose, the dyad is Ej, Ei. Yes.
The question is that one, right? Fij is equal to Fii,
Yeah.
Fij, and
Yeah.
why not?
Why not the other? Yeah.
So if we are multiplying in like the same matrix,
it would be Fij, right? We are not taking transpose, we are just multiplying the same matrix.
Yeah, same it.
Then-
F and F, yeah.
Then we need to iterate the second, the second line. If it is the same matrix, it would be Fi small I into Fi small j, right?
Yeah,
But if we are taking transpose, we have to take take the opposite of first element. Yeah, let's say we are just multiplying the same matrix.
okay,
Then it would be Fij, right?
yes, that is if it's just F and F.
F and F, not transpose, F and F. Then it would be F capital I, a small I, F capital I, small j, capital J, right? That is the sentence for just multiplying the same matrix.
So you're saying this is F and F.
Yes. Yeah. We take different, if it is if it is the same matrix, we take different index for a row for the first matrix and column for second matrix. And the column and the column, the element, the index for column for the first matrix and
Okay, so instead of doing it like that, let's write it out so that whatever you're trying to say, which we can do it. So you're saying, let's consider F dot F.
F dot.
Okay, so what is F dot F? F is F dot F would be F11. This is E1 or EI, EJ. F11, 12, 13, and so on. Okay, actually, I'll do this in index notation. So how would we write F in general? Fij,
Fij,
EI,
E-
EJ. Dot.
then
Then we
same,
need to pick new dummy variables.
Yeah.
We'll call this F, K, K, EK, EK material. Where is this flip in index coming about is the question I'm asking all of you, including myself.
Sorry to interrupt, but it's not visible again.
Okay, yeah, I'm really sorry. Yeah.
Mm.
You're seeing now?
Yeah.
So we are considering F dot F. So if I write F is this, in general Fij, Ei, Ej, and again F is Fkk, Ek. How is this going to be ever same as this is my question. And or in other words, how is this F transpose F? The book does it like effortlessly. They just say, oh yeah, Cij is Fii and Fijj. When I was preparing for this lecture, I kept wrestling over this question, but I couldn't figure it out. That's why I'm putting it in front of the class. I could just say, yeah, the book says it, let's accept it, move on, but I'm not able to. So what are we missing in our understanding about the transpose itself? If the transpose were again this, then it would all make sense. If F transpose is Fij with the dyad vector switched, it would make sense. So consider this. If this is the case, F transpose dot F, this would be Fij, Ej, Ei dot, and then I need F, which I write Fj, K or whatever, Ej, Ek. So this would be Fij, Fjk, Ej, Ei dot Ej, Ek. Would you say that this sequence makes sense? Because now you can do this delta Ij. You can do this delta Ij and write this is Fij, Fjk, Ej, delta Ij. I can just set both of these equal to I, Ek. And I'll swap out the dummy variables and write this is Fi, Fij, Ei, Eg. So what did we learn or relearn today? A transpose it can be interpreted as a transpose of index here, but it is really a transpose of that sequence of dyad vectors. So when you write F transpose, you are not swapping the index here, you are swapping the dyad sequence. It makes sense because think of F transpose, you get Ej, Ei, and you dot it with F itself, which is Ej, Ek. You don't have to do any black magic to just call this delta Ij. The sequence naturally comes out. And then the remaining, this is now a vector, this is now a vector, they become a dyad. Are you with me? Is it making sense? I know this does not warrant a 25-minute discussion, but this is something if you followed the way we have been doing transpose, you will never be able to prove this. This requires some relearning on our part, which is what I'm trying to bring up here. Go back to transpose. A transpose is a transpose or a reversal of the dyad sequence, which kind of comes from what you said. The matrix multiplication will work out only if you reverse the dyads and not the index itself. Okay, so let's clean this up and write everything together. All right, so we have ds squared minus ds squared equal to Fii Fij minus delta Ij dxi dxj. So C is F transpose dot F. If F is written as Fij Ei this implies F transpose should be written as Fij Ei. Now if we calculate C, this would be F transpose Fij Ej Ei dot F. I'll give it new dummy variables. I'll call this Fk K Ek Ek. So I have Fij Fkk Ej Ei dot Ek, which is delta Ia and Ek material. So this gets me Fii Fij Ei Ej material. So we can say Cij, Ei, Ej is this, that makes Cij equal to this. It's a very fine point which it required me to do some relearning, and I hope I conveyed my relearning to you also. Okay, so this one more step, then I'll take the picture. And see, can you see up to this line?
Not the line.
Can you see up to here?
Yeah, yeah.
Okay. I'll stay to the left of that line. So I have right here in this line, I can write this is Cij minus delta Ij dxi dxj. Now you can sleep better tonight, knowing that you didn't just accept what the book said, but you actually reasoned through this. So we have this Cij minus delta Ij. All right. So now we introduce, or they introduce, Eij, or 2 times Eij is equal to Cij minus delta Ij. And this has a name, obviously. E is half Cij minus delta Ij, which is called the Lagrangian strain tensor. We'll come to its interpretation in a second. Strain tensor. Lagrangian strain tensor. Can you see the left hand, like where I am standing?
No, not that one.
Can you see up to this line?
Yeah, you can go a little bit further until EI.
In this one?
Yeah, here. Yeah.
Okay.
Exactly.
All right.
Can I take a picture?
Yeah. Can you see it fully now?
Yeah, yeah. I can see
Oh.
completely until the line.
All right. So then we'll stay to the right of this line, and a little bit to that left of that line. Okay. So now physical interpretation. Consider dx equal to dx1 0 0. What does that mean? We are having a element which is oriented along axis 1, to keep it simple. So then ds squared will only be dx1 dx1. 1, not I, 1. Okay. So you take ds squared minus ds squared. This is Cij minus delta Ij dxi dxj. You can set I equal to j and I equal to 1 because other two directions are irrelevant. So this is basically like writing C11 dx1 yeah. Yeah, minus 1 dx1 dx. It is, you can simply write ds squared equal to C11 dx1 dx1. Now, what is the stretch along direction 1? That would be ds over ds. Change in length, change in position divided by change in length, which will get you C11. Okay. This will be square root of C1. Square root of C11 times dx1 divided by dx1. I'm thinking of ds, not ds squared. So this is square root of C11. You can make the argument that if you put an element along an axis, the components of this C tensor, the components of this strain tensor, the components of the strain tensor basically give you the stretch or change in length for that orientation. So you can consider E11, E12, E13 and so on. At each orientation, it gives you the change in length along that direction due to a loading in the transverse direction if it's an off diagonal term. And if it is a diagonal term, it is the change in length along that direction due to loading in that direction. So E has a direct interpretation of what we generally call as strain, which is change in length divided by length. That interpretation comes exactly to E, not C itself, but C minus delta or C minus identity function. So I'm going to add one more thing here. We consider this alpha 1, right, which is for an element. Remember, this is for an element along the direction 1. And it's purely along 1. That's why we took dx1, 0, 0. Okay. Now, consider dx such that this is dx1, 0, 0 and dy is equal to 0, dy2, 0. What is this dy? It's another element which is oriented along direction 2. So it's like saying here is direction 1, here is dx, and here is direction 2. This is dy2. Okay. And then the question is, this is the initial configuration of your vector or vector. If you subject this to a loading, you are going to get, say, for example, dx and dy. This is the reference. This is the default. How to get dx and dy, or at least the angle between dx and dy. It's like asking if I put a square on a fiber or a fabric, and I subject that to loading in an arbitrary direction, what is the shape change of that square? How do you define a square? The angle between any two sides is 90 degrees. If the angle change, then you go from a square to a rhombus or another shape. how to predict the change in angle. That is the question here. Okay, to do that, how do you calculate angle between two vectors? This is theta cos theta is equal to dx dot dy divided by their magnitude. Right? It's like angle between two vectors or cosine of that angle. Basic idea. So this dx and dy, you can represent this in terms of dx1 or dx and dy, which is the derivation given in page 88, which I hope to get today, but I ran a little slower than I thought. I want you to please look at this. Instead of going through the entire derivation again, on Tuesday, I will quickly summarize that result, assuming that you would have read that page 88. Okay, so take a read and we'll continue this on Tuesday. Okay, and first 15 minutes, we are going to calculate R is equal to FU. So please come for the class and do that quiz. Page 88, please read. We'll continue on Tuesday. Thank you.